ladies and gentlemen. How are we doing today? Good. All right. Take out your computers, put away your phones, put away your headphones, things like that, ladies and gentlemen, and get ready to go today. This isn't helping you what you're looking at, so let me put something up there that would be helpful for you, which is what we're going to be doing today. So there it is, ladies and gentlemen. Get logged in so I can send you a Pear Deck. Isha, we're going to go take that quiz today right away. Okay, so bring your periodic table and something to write with, because that's all you're going to need.
I don't have my periodic table.
Okay, then you
No, I left it out.
to be honest, you probably won't need it for this. I mean, there's nothing on there that you absolutely have to have it for. It was just if you had any notes on it. All right. No, that's okay, because the Pear Deck is just a review. You can get caught up on it. Start. Instruction. That's me. I'll turn the lights on over there for you if you want to head over there. I'll meet you in the room next door. Yep, that one's open. All right, ladies and gentlemen. So take a look at what we're going to be doing today, ladies and gentlemen. And then I will put this into your computers for you. I'm just giving people a minute to get logged in, but then again, it looks like most of you are logged in. So there you go, ladies and gentlemen, and I'll be back in just a second. I need to get a charging block and get Isha going. Okay. So again, with there, the first question, you want to calculate it between all you need to do is put the number on the line that you get your thought. This is the fact that you need to be that conversion. You can do the work down here, whatever, but not create name 2 to 3 things that any measurement shows. And then up here, arrange these units in order from the smallest unit to the largest. When you see the square boxes like this, that means you can pick more than one answer. Okay? So there may be only one answer you can select, however, correct, it's the ovals and the okay. And on the back, it's these 2 tables where you're matching the base unit to the type of measurement mix, or the base unit to the instrument. Okay? Here you go. So you can work on that, and I will get everybody going next door. All right. All right, ladies and gentlemen. Here you go. You are going to need a calculator for the Pear Deck today. So if you don't have one, please come up and grab one, ladies and gentlemen. Also, if you want it, you can use some scratch paper here. Okay. I will put that over by the calculators. I'll put some on the front desk also, because you're going to be doing a little math on our Pear Deck today, ladies and gentlemen. So here we go with our Pear Deck. Before we do that, today we're going to talk about accuracy and precision. We started talking about precision and why it was important yesterday when we were talking about math with sig figs. Today we'll understand better how to get precision, okay? And then tomorrow I've got a lab activity for you to do where you're going to take a bunch of measurements and we're going to work with precision. We'll also talk about accuracy, and then I got a worksheet for you today. If you're missing things, get them done before next week's test. Again, if you're missing homework, you don't have to turn it in to me, okay? Homework doesn't count towards your grade. It doesn't hurt you. If you have a parent, though, who yells about things that are missing in Infinite Campus, you may want to get the homework turned in to me. But understand, it's not going to lower your grade. It's not going to raise your grade. But what it is going to do is it's going to allow you a chance to practice and see the kind of things that are going to be on the quiz or on the test, just so you know. All right? Questions? All right. So here's our first Pear Deck question of the day, ladies and gentlemen. Okay? And it is this. Take and add these 3 numbers together and tell me what we would get in the proper number of sig figs or improper sig figs. I shouldn't necessarily say number because sometimes it's based on a place. So go ahead and do that real quick, ladies and gentlemen. Get an answer and then type it in. And I'm going to get attendance while you are doing that. All right. Let's see. Okay. All right. So, ladies and gentlemen, first of all, when you're doing addition and subtraction, when you're doing these problems, let's go back a step. First thing you got to do is do the math. You got to figure out what the number is that you are supposed to get. Then we'll worry about rounding it. Okay? So we begin by figuring out what number we're supposed to get. So when you add these three numbers together, you get a certain amount of time. After you get that number, then, ladies and gentlemen, now we need to worry about rounding it to a certain either place or number of sig figs. The rule for addition and subtraction is we look at the three measurements that we've taken and we find the least precise measurement. 12.2, 6.31, 14.32. Which one is the least precise measurement, Levi? Which one of those three is the least precise measurement? The first one, 12.2. So that 12.2, ladies and gentlemen, is going to limit our sig figs. Our sig figs have to be in the tenths place because that's what that number is. So when we do this math, ladies and gentlemen, okay, we get 32.83, but we need to round it to the ones place, so that becomes 32.8. Questions? Okay. Any at all? All right, so let's try this one, ladies and gentlemen. Now, this is a common type of problem that you will do in this class. We are taking a mass, which in our lab would go to the thousandths place because that's the place our balances read to. And we would divide it by a volume, and our volumes would normally go to the tenths place because that's the place that our graduated cylinders read to. So this is an accurate type of problem that you would get. Please take and get an answer and round it into the proper number of sig figs, and I will give you just a moment to do that, ladies and gentlemen. Now, when we do this, what kind of number do we get? Is it larger than 1 or less than 1? Less than 1. And here's where you've got to be careful. The rules for multiplication and division are different than the rules for addition and subtraction. Multiplication and division, we look at how many sig figs are in each number. So, Daniela, how many sig figs are in this number right here? 2.568. 4. How many are in 12.1? And we take the smaller number, and that's what our answer goes to. That's what our calculation goes to. But again, you have to be careful because zeros at the beginning of a number are what? Are never significant. So this 0 at the beginning of the number doesn't count. And I got 0.212231405. That's a lot of digits. Most of them have no meaning to a science person. Only the first 3 to this 2 have meaning. So that becomes 0.212 grams per mole, ladies and gentlemen. 3 sig figs, just like Daniela told us, was the smallest amount of sig figs in our problem. Questions? All right. So here we go. We're subtracting 2 numbers, ladies and gentlemen, 2 numbers in grams. Find out what you get and then express it to the proper number of sig figs, please. Are you guys sure you're alive today? This might be the quietest I've ever heard this class. Okay, we'll go with that. All right, addition, subtraction, multiplication, and division. Which one are we doing, Jacqueline? So what do we look for? Do we look for the number of sig figs or do we look for the least precise measurement? Okay, we look for the least precise measurement. Cynthia, of these 2 numbers, 216.3 and 106, which one is the least precise?
106.
Very good. And it only goes to what place? So that 6 is in what place? I'm thinking like tens, hundreds, ones, tenths. What?
Hundreds? Or what?
The 1 is in the hundreds. The 0 is in the tens. And the 6 is in the...
Ones.
See, this is actually the hard part of this, guys. It really is. This is the part that everybody struggles with, whether it's chemistry, chem-com, whatever. We forget those basics of places and a number line and things like this, and all of a sudden you have to go back to them. So you are correct. It is to the ones place, okay? So when we do our math here, ladies and gentlemen, we end up getting our answer, which in this case works out to be, come on, 110.3. That's what we get from the calculator. But we need to round it to the ones place, which means this 0 is where we round it. Now, do we leave this 0 or do we move it up, Rocio? With the number that is after the 0, do we leave it or round it up? We leave it. But I also need to make it significant. Now, I don't want to go any further than that 0. So how do I make that 0 significant? I put a decimal. There is one other way to make that 0 significant. What is it? Anybody? Yeah, but then I changed the number of sig figs, or I changed the place. So I can't do that. You're right. It would be easy to put another 0 after it, right? Because then the zeros at the end would be significant, but now I'd be going to the tenths instead of the ones. What is the only other way to express that number, ladies and gentlemen, so that it is still only precise to the ones place? Yes. Scientific notation, ladies and gentlemen. That would be our only hope on this of doing it another way. Now, again, I don't recommend you having to do that here, and you do not have to do that here. But if you did, ladies and gentlemen, this is what it would be. I don't want to use black because that's obviously not going to show up. You could do 1.10 times 10 to the second grams. Now, again, really, there's no reason to do that. We could put that decimal after the 0, but that would be the only other way to express this number to the proper place. Questions? All right. All right. Last one, ladies and gentlemen. Multiply these 3 numbers together. All right, somebody tell me what we get for a number, please. Somebody tell me what we get when we multiply these three numbers together. The number you got out of your calculator, please.
0.6753054.
What would the unit be?
Centimeters cubed.
Centimeters cubed. Very good. When we multiply these units together, we end up with centimeters cubed. Centimeters times centimeters times centimeters. Okay. How many sig figs in 3.11 here? How many sig figs in that one, Brinley? 3. How many in 0.987, Miro?
3.
And how many in 0.22, Jera?
2.
2. So how many can our answer have, ladies and gentlemen? 2. The second sig fig is the 7, not the 0, the 7. We start with the 6, that's 1, the 7 is 2. So do we leave that 7 or do we move that up to an 8, Jacqueline? We move it to an 8. So your final answer is 0.68 centimeters cubed, ladies and gentlemen. Questions? All right. Excellent, wonderful, incredible, ladies and gentlemen. That's good to go. Now what I need you to do is I need you to take and open your EISN, ladies and gentlemen, and get to... Wait. Sorry, I'm in the wrong one here. There you guys are. Get to slide on accuracy and precision. I know it isn't slide 78 in yours. It is slide 69 in yours, ladies and gentlemen. If you go on to slide 2 and you click this link, it'll take you right there for us, ladies and gentlemen. So that is where you want to be. Today, we're going to start talking about accuracy and precision. Now, please understand this. These are two different terms, two different ways of describing numbers. We can describe accuracy and we can describe precision. So we're going to try to differentiate this for you today, ladies and gentlemen. Okay? Now, in science, when we make measurements, scientists will evaluate both the accuracy and the precision of a measurement. So scientists will look at both, ladies and gentlemen. Let's start with accuracy. Accuracy refers how close a measured value is to an accepted or a known value. Okay? How close a measured value is to an accepted or a known value. What temperature is water supposed to boil at? What temperature does water boil at, ladies and gentlemen? In Celsius, please. I'm sorry. Oh my gosh. I completely forgot, Najma. Or Isha. Sorry. Here you go. There you go. Sorry about that. Okay. What temperature does water boil at in Celsius? Come on. It's exactly 100. Very good. It's exactly 100. Did I tell you the story about Miss Firkin and the 212 at the start of the year? I didn't?
Oh, you did. No, you did.
Yeah, I told where she asked all the teachers what 212 is.
Oh,
She expected we science teachers to know that that's the boiling point of water in Fahrenheit, but we don't measure it in Fahrenheit in science. But 100 is the boiling point of water. So if you take a thermometer and stick it into a pot of boiling water, what temperature do you expect it to read?
100.
100. What if it's reading 95.7? What does that mean?
And is that the starting to cool down or the thermometer going?
What?
Is that the starting to cool down or the thermometer going?
And chances are, if it's in a pot and the water is still boiling,
It's not.
it's not that. Let me rephrase this. How do I want to put this? The thermometer is wrong. The thermometer may not be accurate. Okay? The thermometer may not be accurate. Any instrument, especially digital ones, can sometimes lose their accuracy. They might need to be something called calibrated. Okay? Our balances in the back, every once in a while, you'll hear them make noises. They're doing something called auto-calibrating. They're checking themselves to make sure they're right. Okay. But the only way we can know accuracy is if we have an accepted value, ladies and gentlemen. If we have an accepted value. Now, you guys have life easy. And here's why. You guys have an incredible tool on your desk right now. If you want to look up the density of gold on a Chromebook, you could find it in seconds. If you want to look up the specific heat of silver metal, you can do it. If you want to look up the vapor pressure of water at 24.7 degrees Celsius, you can do it on your computer. This was my Google, ladies and gentlemen. This was my Google when I was in college. Now, they have been printing this book, and they still print it today. This one is the 62nd edition, printed in 1982. But the nice part is this book hardly ever changes, because it's a book of targets, basically. If you want to find the density of gold, it is in here. If you want to find the specific heat of silver, it is in here. If you want to find the vapor pressure of water at 24.7 degrees Celsius, it is in here, ladies and gentlemen. All this book is a list of numbers and targets for you. Okay? Numbers and targets for you. You guys do it on your computer. You guys do it on your computer. By the way, much better because this thing weighed a ton. Okay? This thing weighed a ton and it cost about $85 to $100 to buy. Okay? So nowadays you guys just look values up. But you have to have a target to determine accuracy. And there are times where we will not have a target. We'll be doing a lab and we may not necessarily have a target for it. And there are times where we will. Okay? But examples of things that can be looked up. Density, boiling point. Okay? And for accuracy, you have to compare to the known value. So we said the boiling point of water is 100 degrees Celsius. That's what it is supposed to be. That's what the known value for the boiling point of water is. So if your thermometer that you put in boiling water is reading 100 degrees Celsius, boom, it is right on. But if it's reading 103, it's a little bit off, ladies and gentlemen. It is a little bit off. Okay? That is accuracy. Okay? That is accuracy. Okay? Now, precision is actually two different things, ladies and gentlemen. There are two definitions of precision. One is how close a series of measurements are to one another. How close a series of measurements are to one another. So we're looking at 4 different measurements. We asked 4 of you to go measure the height of the door and you bring me your numbers. Those numbers should be very close together. Maybe not perfect, but they should be very close together. That is the precision of that series, how close together they are. Okay? Now, the nice part about comparing a series of numbers is if you have 2 groups of numbers, you can look at them and determine which one is the more precise by looking at how much difference there is between your numbers. We will show you that in a few moments, ladies and gentlemen. Okay? Now, this is different than the definition we used yesterday, though, isn't it? Yesterday, we talked about the precision of one measurement, right? Which of these measurements is the most precise? We weren't looking at them being close together. That is different. When measurements are supposed to be close together, we can look at the precision of the series of measurements. But we can also look at the precision of an individual measurement, which is how sharp that measurement is. How many places beyond the decimal, or how close to the decimal it gets with its precision. So precision is also how sharp a measurement is. And we'll show you both of these in just a moment, ladies and gentlemen. Precision is determined entirely by the instrument that you use to make the measurement. if we wanted to time something happening in the lab, could we use that clock? Sure, it's got a second hand, right? Okay. So if we wanted to time how long something take, we could figure out how many seconds it took, correct? What place does that clock read to, though? In seconds, what place does it read to? The ones. If we have a stopwatch and we start it and stop it, what place is this reading to, Miro? This is reading to the hundredths of a second, 1.53. Which instrument is more precise? This one, because it goes to the hundredth of a second. So depending on the instrument you are using, ladies and gentlemen, that's going to determine the precision of the measurement that you make. So whenever you grab an instrument, or whenever you choose to use an instrument, or if I put an instrument out there, we have to figure out what the precision of that instrument is, because that's what determines how precise or how sharp your measurement can be. Okay? All right. So we're going to go with how sharp a measurement is, ladies and gentlemen. How far beyond the decimal it goes. So in this yellow set, which letter, A, B, C, or D, is the most precise measurement here, Brenda? Of these four numbers, which one is the most precise? A, B, C, or D? C is the most precise. C is the most precise. Okay? It is the most precise because it goes 3 places beyond the decimal, correct? Thank you. Thank you. Okay, I'll get the lights. Isha, make sure you put away your phone, please. And then we're in your notebook. What slide are we on, just so she knows, please? 70? So slide 70. Okay? So this number only goes to the tenths. This number goes to the tenths. This number goes to the hundredths. This number goes to the thousandths. This is the most precise number out of these four. Okay? How about out of these four? Which is the most precise number, ladies and gentlemen? In the blue set, which is the most precise number? D. D is the most precise number, ladies and gentlemen. D down here at the bottom. Now, if you think about this, ladies and gentlemen, this has a lot more digits than, well, it has more digits that are not 0 than D. Doesn't matter. All that matters is how far beyond the decimal you're going. This goes to 2 places beyond the decimal, or the hundredths. This goes to 3 places, or the thousandths, hundredths. This goes to the 10,000ths. That is the most precise measurement. I don't care that these measurements aren't even close to one another. Of these measurements, this one is the most precise. That's all we're looking for, how sharp the measurement is. Okay? All right, in our orange set, now it gets a little bit trickier. Why? Because there's no decimals. What's that? They all go to the same place. Okay? Now, when you've got numbers like this, ladies and gentlemen, you need to find the last sig fig. 9 times out of 10, where is the last sig fig? No, in any number. In here and in here. Where is the last sig fig? At the very end of a number. There is only one time when that is not true. When is the last digit in a number not the last sig fig? When there are zeros and there are no decimals. Zeros and there are no decimals. In this case, the last sig fig is the 2 in the hundreds place. In this case, it's the 2 in the tens place. In this case, it's the 3 in the ones place. And in this case, it's the 6 in the hundreds. So which of these measurements is the most precise of those four? C. Because C ends up going to the ones place, ladies and gentlemen. That is more precise than going to the hundreds. That is more precise than going to the tens. So these numbers become a little bit tricky. Again, we won't deal with these very often, but we are right now. Questions? All right, green set. Which number is the most precise in the green set, ladies and gentlemen? Which one? D and A?
Yeah.
Absolutely correct. D and A are the two that are the same in precision. They are the most precise measurements there. Questions? Now, yesterday we were looking for what in precision? When we add, subtract. How quickly we forget. Yesterday, when we were looking for precision, we were not looking for the most precise, we were looking for the... So hopefully if you understand precision, you can find that. If we can find the most precise, you should be able to find the least precise as well, correct? Good. Questions? All right. So here is the second way, ladies and gentlemen. Now we expect these numbers to be close together. So now I am asking you, if you compare set A and set B, which of these two sets is the most precise? Now, here is how we determine it, ladies and gentlemen. If we are looking for the most precise measurements, what we are looking for to find this, ladies and gentlemen, is we are looking for the highest and the lowest, and we are going to subtract them, ladies and gentlemen, so that we can find the difference. Okay? So in set A, which number is the biggest number of all of them? 12.6. This is the highest. Which number is the lowest? Okay. So what is the difference between 12.6 and 12.1? 0.5. That's how close these are together. Now let's go to set number B. Now, the numbers in set B compared to the numbers in set A are more precise. Why? They go further beyond the decimal, but that's not what we're looking for here. What is the highest value in set B? This is the highest. What is the lowest? This is the lowest. Now, that is a difference of what? 0.788. Okay, 0.788. Okay. Now, all I needed to know is that this was more than point what? Well, 0.5. Okay, I didn't need to do all the math. I just needed to know, is this more or less than 0.5? Right? So this is obviously more. So what does that mean? It means that set A, ladies and gentlemen, oops, sorry, I'm not on that slide. Set A, ladies and gentlemen, is our more precise measurements. It is our more precise measurements. Good morning, Aiden. Okay. All right. Questions? All right. Take a look at set 2, ladies and gentlemen. Find the difference between the high and low in set C and set D. And then let's see if we can figure out which one is the more precise. Aiden, can you grab your periodic table if you have one? Do you have a calculator? I'll get you one from up here and then something to write with, and we'll get this quiz done that you missed the other day. Okay? And you don't really need if you had notes on your periodic table, that's why you could use it. But if you don't, it's okay because you can do this without it. Most of the stuff on here doesn't have notes. I just need you to bring your pencil. Something to write with. Okay? There's the quiz we took the other day, sir. Okay. 1, 2. you, sir. Thank you. Okay. Sorry, ladies and gentlemen. So here we go. All right. So set C. Daniela, what's the highest value in set C? The one that is the biggest. The highest. Yep. What do we got? 4223. Okay. What's the lowest value in this set? All right. Lowest. So that is a difference of 24, ladies and gentlemen. Okay. Set D. Which one is the biggest number here, Rocio?
38.0.
Okay. And what's the smallest?
12.3.
Okay. Now, real quick, ladies and gentlemen. 38 minus 12. What is that? 26, something like that, right? I'm not even worried about the numbers after the decimal. This is 26, which means what? Okay, so which one is the one that is the most precise set? Set C. There you go. All right, let's take a look at the last one, ladies and gentlemen. Okay, take a look at the last one here. The highest number in set E is what? 0.230, that's the highest. What's the lowest? 0.15, that's the lowest. That makes a difference of about point what? 0.08. Okay. In the next set, in set F, which one is the highest? 16.2. Which one is the lowest? How much is that a difference of? About? It's over 1. It's over 1, right? So what does that mean? That means set E is our more precise set. Questions? Excellent, ladies and gentlemen. Excellent. All right. All right. So probably one of the best ways to illustrate this, ladies and gentlemen, is through archery. Okay, so we just talked about accuracy and precision. How would we describe one arrow right in the center of the target? Accurate. Can we describe precision here? Why not? We don't have more than one arrow. Now we're also making an assumption here, correct?
Yeah.
What is our assumption? Well, that the person was aiming for the middle, right? Now that's a fairly safe assumption with archery, correct? You should be aiming for the middle. Okay. How about over here? What could we say? It is precise. Why?
Because he hit roughly the same spot.
The three arrows are very close together, kind of like three measurements being very close together, correct? How is his accuracy, though? Why? Because he didn't hit the middle. So while they are precise, all their arrows are close together. They are not very accurate because they are not in the middle of the target, right? Okay, good. All right. How about this person? Good accuracy. Why? Because it hit the middle of the target. Good. Keep in mind, accuracy, how close you come to your target. Good precision, you said also, Levi? Why? They're close together. Close together. Okay? And in this case, it would be very hard to have good accuracy but poor precision, right? Because the bullseye is small and they've got to be close together for that. Okay? But in the next one, what could we say? Why?
Because not only are they not close together, but none of them are in the middle.
Very good. Poor accuracy or bad accuracy because none of them are in the middle. Poor precision because none of them are near one another, right? Okay, so one more time here, ladies and gentlemen, let's look at this. 4 friends go golfing, okay? Now, please, in golf, explain to me what par is for a golfer, if you could. And think in terms of what we've been talking about. Think in terms of precision and accuracy. What would par be used for? Nope. Yes. Because par is what now, the purpose of golf is to get the lowest score possible, correct? Okay. But in golf, there is a number of shots that it should take for a person to make the ball in the hole. That is considered par. Okay? Some holes par may be 5, some holes par may be 3. And apparently this is the world's toughest putt-putt golf, ladies and gentlemen, because for mini golf, if you have a par of 72, that is a tough course. Okay? Normally mini golf, the par is like 36. 2 strokes per hole. This is a very tough mini golf course. Okay? But now let's take a look at Jim, ladies and gentlemen. Here's Jim. Okay? So, sorry, let's go back a second. Overall, the par for this course is 72. That's the target that people are trying to hit, 72 or lower. Okay? That's our target. So here's Jim. Here's Jim's score on every hole on the front 9, every hole on the back 9. What do you notice about his scores? What can you tell me about Jim's scores, Jara? The numbers, at least.
Like they're larger than they would be.
Okay, but when you compare the numbers, 6, 6, 6, 5, 6, 6, 5, 6,
They're fairly close together.
I would say they're fairly close together. Correct. Okay. Okay, if the numbers are fairly close together, what are we describing then, ladies and gentlemen?
Precision.
And what would we say about Jim's precision?
It's good.
Okay, and again, we'll just use good and bad. Okay, I would say it's good because all his numbers are close together. They're not all the same, but they're all very close together, right? Okay, so now let's look at the second part. What was Jim's total score? 104. Now his target score was supposed to be,
72.
so would you say that 104 is close to 72?
No.
So what does that tell us about Jim's accuracy? Okay, so Jim had good precision. His numbers were all close together, right? But he had bad accuracy because his total wasn't near what it was supposed to be, correct? Okay, let's take a look at Cindy. Look at her individual scores on every hole. When you look at those scores, what do you notice and what does it mean? What do you notice about Cindy's scores on each of the 18 holes?
They are generally close together.
They are or are not?
Aren't.
They're kind of all over the place, aren't they?
Yeah.
High of an 8, low of a 2. That's a pretty big range, right? 6s, 7s, 4s. Same thing over here. High of an 8, low of a 3. So what would we say about Cindy's precision?
She's not precise.
I would say her precision is bad. I would agree with that. That's bad precision. How about her accuracy? She shot a 92. She was supposed to shoot a 72.
Also pretty
I would agree. That is not the greatest. Okay, that is not the greatest. That would be bad. All right, now let's take a look at Victor. What do you notice about Victor's scores on each hole, Brenda?
They're almost all close.
Okay, so what does that mean? If your score is almost always the same, what are we saying? Are we describing precision or accuracy? And would we say it's good or bad? We would say it's good. Now look at Jim's total score. Daniela, what was his total score?
104.
Nope. I'm sorry. Oh, I'm sorry. I said the wrong name. Victor. We're talking about Victor here. Sorry.
73.
And what's his target?
72.
Is that good? I would say that's very good. I'd be thrilled with that, ladies and gentlemen, if that were my score. All right, take a look at Susie. Last one. Jacqueline, what would you say about her scores on each hole? Are they close together or are they far apart? Okay, which means what for precision or accuracy?
The precision is best.
Her precision is bad. Look at her total though. 72. What was her target?
72.
So what does that say about her accuracy?
It's really good.
Good. All right, ladies and gentlemen. So if we look at this, look at the combinations. What does that mean, ladies and gentlemen?
It's hard to do both.
What?
It's hard to be precise and accurate.
Can you be, though, precise and accurate?
Yeah.
Okay?
A variety of different things to mix that you could be.
Okay, so what does that tell us about these two ways of looking at things? Let me rephrase the question. If you have good accuracy, does that mean you're going to have good precision?
No.
They aren't dependent on each other.
Thank you. They are not dependent on each other. These are two individual ways of describing something. Okay? Kind of like describing your height and your weight. Okay? Your height and your weight. If you are tall, does that mean you are going to weigh, that you're going to have a heavy weight? No. You could be tall and very thin, right? You could be short and very heavy. There are two different ways of describing a person. Just because one is one way doesn't mean the other is going to be the same. Same thing here. Precision and accuracy, different ways of describing numbers. You can have good precision and bad accuracy. You can have good precision and good accuracy. Two different ways of looking at things. Questions? Okay. All right. Now, we're going to get into this today, and then I'm going to give you some time to work on your worksheet in just a few minutes. But whenever you take a measurement, ladies and gentlemen, you are required to estimate one place beyond the precision of the instrument. We said precision was determined by the instrument you used to take a measurement. Okay? So let's talk about that for a second. In precision, we're talking about a place here. We're talking about hundreds, tens, ones, tenths, hundreds, thousands. That's what we're talking about. Okay? So we're talking about the number of places. The one exception to this rule is a digital instrument. With a digital instrument, you just write down every digit that is shown on that digital instrument. You do not add any, you do not take any away. If it ends 0.000, you write 0.000. Digital instruments, you do not have to add a place to. That is the one exception. So digital instruments make life easy, ladies and gentlemen. They really do. Okay? To find the precision of an instrument, you need to find where all the consecutive values of a place are shown. Each instrument used to measure has its own precision. Markings representing every 5, 10, or every 2, 5, or 25 do not offer any more precision. Okay? They do not offer any more precision, ladies and gentlemen. Okay? So, let me explain what we mean. I've got a picture here on the next slide for you. This is a thermometer, ladies and gentlemen. What unit is it reading in? What unit?
Oh, Celsius.
Celsius. So always look, always know what unit you're going to talk about. Okay? Now, we can clearly see that the thermometer is marked off in what place? Well,
Clearly 10.
more clearly tenths. So again, we start with the numbers that are on there, or the bigger marks that are on there. There's 10, 20, 30, 40, 50. That's the tens place, correct? Now the question you ask yourself is between 10 and 20. Are there enough marks so that you can find 11, 12, 13, 14, 15, all the way to 19? Are there enough marks here? Yes. So now we're in the ones place. Now, between 11 and 12, are there any marks on this?
No.
So what place is this reading to? This is reading to the ones. This is reading to the ones. So our rule says when you report an answer, you go one place beyond the place you are sure of. What is one place beyond the ones? The tenths. So in other words, right here, this level, ladies and gentlemen, what is it very close to? What number?
Right.
It is close to 25. Is it closer to anything else?
I think it's closer to 24.
I think it's probably somewhere in between 23 and 24. Can we agree on that?
Yeah.
Okay. So now we know it's more than 23, right? We know it's less than 24. Give me a number in the tenths place between 23 and 24, Cynthia. Any number to the tenths place between 23 and 24. 23.5, 23.6, 23.7, 23.8, right? 23.1. That is the number that you are going to report. Something to the tenths place. Now, you get to pick what place or what digit you think that is. Now, is this closer to 24 or 23? If you had to judge, would you say it's closer to the 24 mark or the 23?
24.
Okay, so our number needs to be closer to 24 than 23. So 23.1 probably not going to work here, right? Would 23.9?
Yeah.
What if you think it's right at that 24 line?
Can't you just say the 24 then?
Okay, but that's not to the tenths place, is it?
24.0.
We could say 24.0. We could say 23.9, 24.0, 24.1. Which of these is correct?
24.0. All of them are correct.
All of them are correct. Wait a minute. All of them are different, though.
Yeah, but they're all saying the same thing, like it's close to 24.
Okay, you remember the three things shown in every measurement?
Uncertainty and precision.
Uncertainty and precision. When we look at these numbers, because they're going to the tenths place, what place did our instrument read to?
Or well, we don't know that.
We do know that.
The ones.
Read to the ones, because you are required to go one beyond that, correct? So what place did our instrument read to? The ones. That's telling us precision. Which one of these is correct? All three of them. That's uncertainty. Why? We got three different numbers for the same reading, and all of them are good. Why? Because that's right about at 24. So maybe Cynthia writes down 23.8. Maybe Nadia would write down the same number. Anyway, Miro, you write down 23.9. Brinley writes down 24.0. All of them are correct. All of them are correct, even though there is slightly different. That's uncertainty, ladies and gentlemen. That's the third thing shown in any measurement. Okay? All of these answers are acceptable because you can estimate in the tenths place. All right. What place is this ruler reading in? What place? What's it marked out in?
Centimeters.
Okay, centimeters is our unit. We're going to get this straight yet, guys. I switched the question up this time. The unit is centimeters. What place is that instrument reading into? What are the marks on it? The ones. Is there anything between 8 and 9? Okay, so it isn't going to the tenths place, correct? But our instrument is reading to the ones place, which means our number that we report has to be to the tenths place, one beyond that. Okay? Now, that line is very close to what number?
8.
So how could we write the number 8 to the tenths place?
8.0.
Okay, what else could we do?
Or 7.9 or 8.1.
Yeah. Okay? Since the ruler reads to the ones, we have to measure to the tenths. That's the rule. We got to go one beyond it. Okay? So that line looks like it's right on the 8. I've got to find a way to write 8 to the tenths place. That means that I can write 8.0. I could write 7.9. I could write 8.1. Okay? I could write 8.1. Questions? All right. I don't know if I can do this, but we're going to try, ladies and gentlemen. Go ahead. What was your question going to be? Okay. All right. So I'm going to make a new line here, ladies and gentlemen. It will not be the straightest line in the world. All right. That line right there, the red line. What two numbers is it between?
3 and 4.
It's between 3 and 4, right? So now, if we were writing this measurement, we need to pick a number between 3 and 4, correct? Okay, give me a number between 3 and 4 to the tenths place.
3.5.
3.4, 3.5, 3.6. Could we do 3.1?
No.
No,
Why not?
because it's too close to 3.
It's pretty much in the what?
In the middle.
Okay. So again, we're allowed to estimate. We're not allowed to go crazy here. This is a pretty big gap, right? And we can see that it's pretty close to the middle. So maybe 3.3, maybe 3.4, maybe 3.5. I'm good with all of those. Could we say that's 3.9?
No.
No, because it would have to be somewhere over here, right? Now, where this becomes difficult is if your lines become what?
Small.
Closer together.
Oh.
Closer together. And I think that's what you meant by small. If the gap in between them is small, it becomes harder to estimate. But the good news is it also becomes harder for someone to argue with you. So when the lines are small, just make sure you're getting to the right place, ladies and gentlemen. Even if you end your number 0.0. Because if the lines are close together, really close together, it's going to be hard for somebody to argue with you. Okay? But you got to get your number into the right place. That you have to do. That is not an option. Okay? All right. I don't want to do that. Get away from there. There we go. Now we can do that. Okay? All right. A beaker. Something we've commonly used in the lab before, right? What place is that beaker reading in? This beaker right here. What? Hundreds. 100, 200, 300, 400, 500. Now be careful. A lot of times beakers will have a mark in between here. Nope. Hold on. So if there's a mark in between there, what would that represent? Halfway. What's halfway between 100 and 200? But 50s doesn't help us. Unless we've got 10, 20, 30, 40, 50, 60, 70, 80, and 90. The 50s may help us estimate, but it doesn't add any more precision. Okay? It doesn't add any more precision. So this is in the hundreds place, right? We read to the bottom of this. What is this called again? Anybody remember? Where meniscus. Liquid has that curved shape on the bottom. We read to the bottom of it, so we know for sure it's between what two numbers, Rocio? That line right there is between what two numbers? 400 and 300. So now, we need to pick a number to what place? If it reads in the hundreds, we go to the wrong way. Tens. 10s. 10s. Because this is reading in 100. 100. We go to the tens place. Okay, pick a number between 300 and 400 in the tens place, please. 350. Anybody else?
330, 360, 370.
Yeah. And we can be around there a lot, right? 330, 340, 350, 360, somewhere in there. Do not do 345. Okay? Do not do 355. That would tell someone that we know for sure where the tens place is. We don't know that here. You only can go one more place than the precision of the instrument. Okay? One more place than the precision of the instrument. All right, so this is a graduated cylinder now. Again, 30, 40, there's the tens place. Any marking smaller than the tens? Well, 31, 32, 33, 34, 35, 36, 37, 38, 39. So that's the what place? So what place does our answer have to be to? Can you hang? Yeah, go ahead. What? To the tenths. If it reads in the ones, we're going to the tenths. All right, where's that mark come right out at? Or where's that water level come right out at? So how do we write 35 to the tenths? 35.0. 34.9, 35.1, anything like that. Anything like that. And don't forget the unit, milliliters, ladies and gentlemen. Questions? All right. All of these are acceptable as long as your estimated is in the tenths place. All right. We'll get to that in a minute. All right. You've got about 10 minutes, ladies and gentlemen. Let's take a look at the worksheet that you have due today or tomorrow, ladies and gentlemen. Google Classroom, classwork. This will not take you long. Accuracy and precision worksheet, ladies and gentlemen. Accuracy and precision worksheet. Okay, so here's your target, 100 degrees Celsius. Okay, you've got 4 measurements. You want to know which one is the most accurate. So when we look at this, ladies and gentlemen, which 2 numbers can we eliminate right away? Well, what's our target?
100.
Okay. So which of these two numbers can we eliminate right away? 98.6. Why? Well, but it could be doing that, right? The thermometer could be reading that, but it's further away from 199.6, right? So it can't be this one. This is closer to 100. Which other one gets eliminated? 101.3. Why? Because it's further away than this one if we're on the high side. Accuracy doesn't matter if you're high or low. What matters is which one is closest. Okay? So, of these two numbers, 99.6 and 100.3, which one is closer to 100? Yeah, because it's only off by what? 0.3. That's how you determine which one is the most accurate measurement, ladies and gentlemen. Which of the numbers that I'm giving you is closest to your target one? Okay? So in that yellow box, you just need to type in the one measurement that is the most accurate. So, give you a little hint here, ladies and gentlemen. If you highlight the number, because you don't want to do the unit, you want to highlight it all and copy and paste it. I'm a huge fan of copying and pasting. You can hit Control C, but if I copy this in here, what color is it going to be?
White.
So, little trick, ladies and gentlemen. If you do Control Shift V, it will do the formatting of whatever that box is set for, instead of the formatting of how you copied it. It's your choice. How do I make this 0 into, or that O into a degree sign again? Control what? Period. Yes, that's how I make the degree Celsius sign, if you need to know, ladies and gentlemen. I use the letter O, lowercase o, and I make it a superscript with the control and the period key. Okay? So here, ladies and gentlemen, again, the same thing. Now, which of these measurements is the most precise or the sharpest? So now you're looking at these four measurements and you're comparing their precision. Just the four of them. Which one is the sharpest? You write it in this box. So for this one, which one of these four numbers is the sharpest above? Not the closest. We have no target that we're going for. Which one is the sharpest measurement? 700 nanometers, 710 nanometers, 680 nanometers, or 691? 691 nanometers, because it goes to the tens place. It goes to the ones place. Okay? And then here, ladies and gentlemen, now I'm asking you to find the range of these four measurements. In other words, take the high, take the low, subtract them. Excuse me. Thought I was going to sneeze. Find the range. That's what we were doing earlier. What is the difference between the high and the low? Put it here, here, and here. And then tell me which of the groups, A, B, C, or D, is the most precise. Okay? All right, ladies and gentlemen. Go to work. If you have questions, you can ask. Call me over. I will give you a hand if you need it. Celsius, hit Control and the period key. Type in a lowercase o. Hit Control and the period key again. Type in a capital C. Yes. Wow. He's got to work on a budget. He's got like 12 kids. Oh, maybe that's Philip Rivers. You're welcome. Yes, Cynthia. I'm sorry. Well, it's the highest minus the lowest. Okay. If you get a negative number, consider it like an absolute value. In other words, you can just call it 70 if you get minus 70. But now here, I'm looking at that. No, you did it right. So you have 2130
and 2,200.
Couldn't get
That
the
is-
circle up there.
You're right, you did put it into your calculator,
I did the
reverse,
control period.
but again, it doesn't matter, you're just looking at how big it is, it doesn't matter if it's minus 70 or positive, take it as an absolute value. Okay?
Okay.
Okay, I got it.
The one that has the smallest range, the one where they're closest together, so that's why we're asking you to do the range, so you can see how far apart the numbers are. And then the one where they're closest together, that'd be the most precise, yes, yes.